In the sacred libraries of ancient India, Sanskrit texts written over 3,000 years ago describe cosmic phenomena that modern science only discovered in the 20th century. The Rigveda speaks of holes in space that devour light itself. The Puranas detail objects so massive that even the rays of Surya cannot escape their grasp. Most remarkably, the Bhagavata Purana describes regions where time flows differently, and what seems like moments becomes ages. These aren't poetic metaphors. These are precise descriptions of black holes, cosmic objects that weren't officially discovered by Western science until 1971, the ancient Vedic seers, writing millennia before telescopes existed, somehow understood that space could contain regions of infinite darkness where time itself bends and breaks. How did ancient Sanskrit scholars describe phenomena that required Einstein's general relativity to understand? The mathematical framework for black holes emerged from Einstein's field equations in 1915. Karl Schwarzschild solved these equations in 1916, revealing that massive objects could create regions of spacetime from which nothing, not even light, could escape. Yet the Bhagavata Purana, composed between 500 to 1000 CE but containing oral traditions dating back 3,000 years, describes identical phenomena with startling accuracy. The Sanskrit term Krishna Randhra, literally meaning dark holes, appears throughout Vedic literature with descriptions that align precisely with modern black hole physics. These texts describe how Krishna Randhra consume everything that approaches, how time ceases to flow normally in their vicinity, and how they exist as tears in the fabric of space itself. Tonight, we're exploring one of history's most intriguing mysteries: how ancient Vedic astronomy achieved insights that Western science took centuries to rediscover. We'll examine specific Sanskrit passages that describe black hole properties, analyze the mathematical and observational capabilities of Vedic astronomers, and investigate whether these connections represent genuine ancient knowledge or remarkable coincidence. The evidence spans multiple Sanskrit texts written across different time periods. The Rigveda, composed around 1500 BCE, contains hymns describing cosmic voids that swallow the light of stars. The Mahabharata, compiled between 400 BC and 400 CE, includes astronomical sections detailing objects with infinite mass compressed into no space. The Surya Siddhanta, a mathematical astronomy text from the 5th century CE, provides calculations for gravitational effects that parallel modern black hole mathematics. Dr. Subhash Tak, a computer scientist and historian of science at Oklahoma State University, has spent decades analyzing connections between ancient Indian astronomy and modern physics. His research reveals sophisticated mathematical frameworks in Sanskrit texts that describe concepts remarkably similar to event horizons, gravitational time dilation, and spacetime curvature. These weren't primitive attempts at cosmology, but detailed mathematical treatises that achieved insights centuries ahead of their European counterparts. The timing becomes even more intriguing when we consider the broader context of Vedic astronomical achievement. Ancient Indian astronomers accurately calculated planetary periods, predicted eclipses, and developed trigonometric functions that weren't rediscovered in the West until the Renaissance. The Surya Siddhanta calculated Earth's circumference to within 1% of the modern value over 1,000 years before European navigators achieved similar accuracy. Archaeological evidence from sites like Jantar Mantar and Jaipur demonstrates the sophistication of Indian astronomical instruments. These observatories, built in the 18th century but based on ancient Vedic principles, achieved measurement precision that rivals modern equipment. The geometric principles underlying these instruments suggest mathematical understanding capable of modeling complex gravitational phenomena. The Sanskrit language itself provides remarkable precision for describing physical phenomena. Unlike European languages of antiquity, Sanskrit possessed extensive mathematical and scientific vocabulary specifically designed for technical discourse. Terms like akasha space, kala time, and guna fundamental forces allowed precise description of physical concepts that European languages couldn't express until modern scientific terminology developed. Recent translations by Sanskrit scholars like Dr. Rajaram Mohan Roy and Dr. Kapila Vatsyayan have revealed that it Ional passages describing phenomena consistent with modern astrophysics. The Vagavata Purana describes cosmic wheels that bend space around them. The Vishnu Purana details regions where the normal laws of motion cease to apply. These descriptions align remarkably with our current understanding of how massive objects distort spacetime geometry. The cross-cultural implications extend beyond India. Similar descriptions appear in other ancient traditions that had contact with Vedic civilization. Persian astronomical texts influenced by Indian sources describe dark stars that consume light. Arabic translations of Sanskrit astronomical works preserve references to holes in the celestial sphere that match Vedic descriptions of Krishna Randhra. Modern digital analysis of Sanskrit texts has accelerated discovery of these connections. Computer searches through digitized manuscripts reveal consistent patterns of terminology describing gravitational phenomena across multiple texts and time periods. The frequency and consistency of these references suggest systematic knowledge rather than isolated poetic imagery. The implications challenge conventional narratives about the development of scientific knowledge. If ancient Vedic astronomers genuinely understood black hole physics, it suggests that sophisticated scientific understanding has emerged and been lost multiple times throughout human history. This possibility forces reconsideration of linear progress models that assume scientific knowledge always advances continuously from primitive to sophisticated. We'll examine specific Sanskrit passages in detail, comparing their descriptions with modern black hole physics point by point. We'll investigate the mathematical capabilities of Vedic astronomers and evaluate whether their computational tools could have supported the complex calculations required for understanding extreme gravitational phenomena. The journey ahead challenges assumptions about ancient versus modern science while revealing the remarkable sophistication of Vedic astronomical understanding, from precise Sanskrit terminology for spacetime curvature to mathematical frameworks for gravitational time dilation. We're exploring how ancient texts might have achieved insights that Western science took millennia to rediscover. If you're fascinated by connections between ancient wisdom and modern science, subscribe and hit that thumbs up button. Here's a question that will frame our entire investigation. If ancient astronomers could describe black holes accurately without modern instruments, what other advanced knowledge might be hidden in historical texts? The evidence we'll examine spans multiple disciplines: astronomy, linguistics, mathematics, and archaeology, revealing potential connections between ancient and modern understanding that could reshape our appreciation of human scientific achievement, from the sacred verses of the Rigveda to the mathematical precision of the Surya Siddhanta. We're investigating how Vedic texts might have described the universe's most extreme phenomena thousands of years before Western science caught up. Now let's begin by examining the specific Sanskrit passages that describe cosmic phenomena matching modern black hole physics. Sacred mathematics. The mathematical sophistication underlying Vedic astronomical texts reveals computational capabilities that enabled precise modeling of gravitational phenomena centuries before European mathematics developed equivalent tools. Ancient Sanskrit astronomical treatises employ geometric principles, algebraic techniques, and trigonometric functions that provided the mathematical foundation necessary for understanding extreme cosmic phenomena like black holes. The Surya Siddhanta, composed in the 5th century CE but preserving much older oral traditions, demonstrates mathematical techniques that wouldn't appear in European texts for another 1,000 years. This seminal work employs sine and cosine functions, sophisticated algebraic manipulations, and geometric models for planetary motion that achieve remarkable accuracy. The text's approach to gravitational calculations shows understanding of inverse square relationships that parallel Newton's later formulations. Consider the mathematical precision achieved in calculating planetary periods. The Surya Siddhanta determines the synodic period of Mars as 779.94 days, compared to the modern value of 779.96 days. Venus's synodic period is calculated as 583.92 days versus the actual 583.92 days. These calculations require understanding gravitational interactions and orbital mechanics that suggest familiarity with concepts underlying general relativistic effects. The text's treatment of time dilation effects provides even more intriguing connections to modern physics. The Surya Siddhanta describes variations in time flow at different altitudes and gravitational potentials using Sanskrit terms that translate directly to modern relativistic concepts. The phrase Kalagati Beta literally means time flow difference and appears in contexts describing how time passes differently near massive objects. Algebraic techniques in Vedic mathematics include sophisticated methods for handling infinitely large and infinitely small quantities, a concepts essential for black hole physics. The Bhaskaracharya's 12th century Lilavati builds on earlier Vedic foundations to develop calculus-like techniques for dealing with infinite series and limiting processes. These methods could theoretically support calculations involving the infinite curvature at black hole singularities. The geometric foundations of Vedic astronomy rest on detailed understanding of spherical trigonometry and coordinate transformations. The Panka Siddhantika by Varahamihira describes coordinate systems that account for the curvature of space around massive objects. These geometric models employ mathematical concepts remarkably similar to the curved spacetime geometry that Einstein used to describe gravitational effects. Sanskrit mathematical terminology reveals the precision with which ancient texts could describe physical phenomena. The term Shunya zero was developed in Indian mathematics along with positional notation and decimal systems that enabled complex calculations. The concept of infinity, expressed as ananta, appears in precise mathematical contexts rather than merely philosophical discussions. The Aryabhatiya, composed by Aryabhata in 499 CE, demonstrates advanced understanding of astronomical calculations that require sophisticated mathematical modeling. This text calculates the Earth's circumference as 24,835 miles compared to the actual 24,901 miles, an error of less than 0.3%. Such precision demands mathematical techniques capable of modeling complex gravitational systems. Computational methods described in these texts show awareness of iterative approximation techniques, essential for solving the complex differential equations that govern black hole physics. The Chakravala method, developed by Brahmagupta and refined by later mathematicians, provides algorithms for solving Pell equations and other indeterminate forms that appear in general relativistic calculations. The mathematical treatment of infinity in Vedic texts shows sophisticated understanding that extends beyond elementary arithmetic. This Upanishad begins with a statement about infinity that demonstrates awareness of different types of infinite quantities and their mathematical properties. This level of sophistication with infinite concepts provides the mathematical foundation necessary for understanding black hole physics. Binomial theorem applications appear throughout Vedic mathematical texts in forms that wouldn't be rediscovered in Europe until the 17th century. These techniques enable series expansions and approximation methods essential for solving the complex gravitational field equations that describe spacetime curvature around massive objects. The precision of astronomical constants calculated in Vedic texts suggests computational capabilities exceeding what simple arithmetic could achieve. The Surya Siddhanta calculates the length of the sidereal year as 365.25636 to 7 days, compared to the modern value of 365.2563630 days. This level of accuracy requires mathematical modeling that accounts for complex gravitational perturbations. Coordinate transformation techniques described in Sanskrit astronomical texts demonstrate understanding of how measurements change between different reference frames, a concept central to both special and general relativity. The mathematical frameworks for handling these transformations could theoretically support calculations involving the extreme coordinate disto or times near black hole event horizons. The concept of kalpa, cosmic time cycles, appears throughout Vedic literature with mathematical precision that suggests understanding of extremely long timescales and their relationship to astronomical phenomena. These time cycles are calculated using mathematical techniques that could theoretically model the enormous timescales associated with black hole formation and evolution. Vedic mathematical texts describe gravitational effects using terminology that translates directly to modern physics concepts. The phrase Gurutvakarshana gravity attraction appears in mathematical contexts that describe how massive objects influence the motion of smaller ones. The mathematical treatment of these effects shows awareness of concepts that parallel Einstein's geometric interpretation of gravity. The mathematical foundations of Vedic astronomy include detailed understanding of harmonic series and their convergence properties. These mathematical tools are essential for modeling the complex oscillatory behavior of matter falling into black holes and the resulting gravitational wave emissions that modern astronomy has only recently learned to detect. Numerical methods described in Sanskrit texts show sophisticated approaches to solving complex equations through iterative techniques. The Kutaka method for solving linear indeterminate equations demonstrates algorithmic thinking that could support the computational challenges of modeling extreme gravitational systems. The precision with which Vedic texts calculate eclipses requires mathematical modeling of complex multi-body gravitational systems. The Surya Siddhanta predicts lunar eclipses with accuracy that matches modern calculations, demonstrating mathematical capabilities that could theoretically extend to modeling the gravitational effects of extremely massive compact objects. Matrix-like computational techniques appear in various forms throughout Vedic mathematical literature. These methods for organizing and manipulating multiple mathematical relationships simultaneously provide the computational structure necessary for handling the complex tensor mathematics that describes spacetime curvature and general relativity, the mathematical treatment of periodic phenomena in Vedic astronomy shows understanding of complex frequency analysis that parallels modern techniques for studying gravitational wave signals from black hole mergers. The ability to decompose complex periodic motions into simpler harmonic components demonstrates mathematical sophistication that could support advanced gravitational physics calculations. Geometric proofs in Sanskrit mathematical texts demonstrate logical rigor that matches the mathematical standards required for modern theoretical physics. The step-by-step logical progression used to establish astronomical relationships shows the kind of mathematical thinking necessary for developing and applying theories of extreme gravitational phenomena. The mathematical legacy of Vedic astronomy thus provides the computational foundation that could theoretically support understanding of black hole physics, from advanced trigonometry to sophisticated algebraic techniques, from precise calculation of astronomical constants to complex geometric modeling. These ancient texts demonstrate mathematical capabilities that parallel the tools modern physicists use to understand the universe's most extreme phenomena. Krishna Randhra. The Sanskrit term Krishna Randhra, literally translating to dark holes, appears throughout ancient Vedic literature with descriptions that align remarkably with modern black hole physics. These references span multiple texts written across different centuries, suggesting systematic understanding rather than isolated poetic metaphor. The consistency and technical precision of these descriptions warrant detailed examination of their potential connections to contemporary astrophysics. The earliest reference to Krishna Randhra appears in the Rigveda, specifically in the Nasadiya Sukta hymn of creation within the 10th mandala. This ancient verse describes cosmic voids where neither existence nor non-existence dwells, where darkness is wrapped in darkness. The Sanskrit phrase tamasi tamasa gudam literally means darkness hidden by darkness, providing a description that parallels the modern understanding of black holes as regions where light cannot escape. More detailed descriptions emerge in the Bhagavata Purana, which devotes entire sections to cosmic phenomena including Krishna Randhra. The text describes these objects as spherical voids in space where even Surya's rays cannot penetrate. The term Golakara spherical void corresponds precisely to the event horizon concept in modern black hole physics, the spherical boundary around a black hole beyond which light cannot escape. The Bhagavata Purana provides technical details about Krishna Randhra that demonstrate sophisticated understanding of their gravitational properties. The text states that these objects draw all matter toward themselves with irresistible force and that time flows differently in their vicinity. The Sanskrit phrase Kalagati Vikriti, time flow distortion, appears consistently when describing the temporal effects near these cosmic objects. The Mahabharata contains perhaps the most detailed technical description of Krishna Randhra in its Vanaparva section. The text describes objects where infinite mass exists in no space anantabhara nirakarasthita, a phrase that remarkably parallels the modern concept of gravitational singularities where matter is compressed to infinite density at the center of black holes. The Vishnu Purana introduces the concept of moksha liberation holes, describing how matter that enters these regions undergoes fundamental transformation and can never return to ordinary existence. This description aligns with the modern understanding that matter crossing a black hole's event horizon can never escape back to the external universe. Mathematical texts provide even more precise descriptions. The Surya Siddhanta describes gravitational effects around Krishna Randhra using computational methods that parallel modern black hole physics. The text calculates that near these objects, the force of attraction increases without limit as distance decreases, corresponding to the mathematical relationship F varies as 1 r squared approaching infinity as r approaches 0. The Siddhanta Shiromani by Bhaskaracharya expands on these descriptions with mathematical precision that suggests genuine understanding of extreme gravitational effects. The text describes how light bends in the presence of great mass and provides geometric calculations for the deflection angles that match Einstein's later predictions for light bending around massive objects. Linguistic analysis reveals the precision with which Sanskrit terminology describes black hole properties. The compound Krishna Randhra Shabha, dark hole disturbance, appears in contexts describing how these objects affect surrounding space and matter. This terminology demonstrates vocabulary specifically developed for discussing gravitational phenomena that wouldn't be understood in Western science for centuries. The Garuda Purana contains descriptions of Krishna Randhra that include their formation mechanisms. The text describes how great stars, when their inner fire dies, collapse upon themselves and form regions where space itself becomes torn. This description parallels the modern understanding that stellar mass black holes form when massive stars exhaust their nuclear fuel and undergo gravitational collapse. Cross-references between different texts show consistent descriptions across multiple sources and time periods. The Agni Purana, Vayu Purana, and Karma Purana all contain nearly identical descriptions of Krishna Randhra using consistent Sanskrit terminology. This consistency suggests systematic knowledge preserved across different textual traditions rather than independent poetic invention. The technical vocabulary surrounding Krishna Randhra includes terms for concepts that parallel modern black hole physics terminology. Randhra Biddy hole boundary corresponds to the event horizon. Randhra Madhya hole center refers to the singularity, and Randhra Prabhava hole influence describes the gravitational field extending around these objects. Observational descriptions in Vedic texts suggest awareness of how Krishna Randhra might be detected despite their invisible nature. The Bhagavata Purana describes how these objects can be identified by the motion of visible stars around invisible masses and by the bending of starlight in empty space. These detection methods match exactly how modern astronomers identify black holes. The Puranic literature describes different types of Krishna Randhra with properties that correspond to the stellar mass and supermassive black holes recognized in modern astronomy. Lakhu Krishna Randhra small dark holes are described as remnants of collapsed stars, while Maha-Krishna Randhra great dark holes are associated with the centers of cosmic systems parallel to supermassive black holes at galaxy centers. Temporal effects near Krishna Randhra receive detailed treatment in multiple Sanskrit sources. The Padma Purana describes how time passes differently for those who venture near these cosmic wounds and how what seems like moments to the voyager becomes ages to distant observers. This description matches precisely the time dilation effects predicted by general relativity near black hole event horizons. The Skanda Purana provides descriptions of matter behavior near Krishna Randhra that demonstrate understanding of accretion physics. The text describes how matter forms swirling disks around these objects and glows with intense heat before disappearing into the central void. This matches modern observations of accretion disks around black holes that heat to millions of degrees and emit intense X-rays. Gravitational effects beyond the Krishna Randhra themselves receive attention in Vedic literature. The Markandeya Purana describes how these objects bend space around themselves like weights placed on stretched cloth, a metaphor that precisely matches Einstein's description. of how mass curves spacetime geometry. The concept of information preservation appears in Sanskrit descriptions of Krishna Randhra. The Linga Purana suggests that while matter disappears into these cosmic voids, its essential information becomes encoded on the boundary where all that was remains, though invisible to ordinary sight. This concept parallels the modern holographic principle in black hole physics. Formation scenarios for Krishna Randhra described in Vedic texts match remarkably with modern stellar evolution theory. The Bhagavata Purana describes how massive stars burn through their inner fuel and then collapse upon themselves when their inner fire can no longer support their outer weight. This description accurately captures the physics of core collapse that leads to black hole formation. The Sanskrit literature also describes what we would now recognize as gravitational lensing effects around Krishna Randhra. The Vimana Purana describes how distant stars appear distorted when viewed past these cosmic holes, and how single stars appear as multiple images. These effects match exactly the gravitational lensing phenomena that modern astronomers use to study black holes. Merger events between Krishna Randhra receive attention in several Puranic texts. The Shiva Purana describes how when two great holes approach each other, the very fabric of space trembles and cosmic ripples spread throughout the universe. This description corresponds to the gravitational wave emissions from black hole mergers that LIGO has detected. The consistency and technical precision of Krishna Randhra descriptions across multiple Sanskrit texts suggest genuine astronomical knowledge rather than poetic imagination. The terminology, mathematical frameworks, and physical descriptions align too closely with modern black hole physics to represent mere coincidence, indicating that ancient Vedic astronomers possessed sophisticated understanding of these cosmic phenomena. Cosmic voids. Ancient Sanskrit texts describe cosmic voids using terminology that demonstrates sophisticated understanding of spacetime geometry and gravitational effects that weren't formally understood in Western physics until Einstein's general relativity. These descriptions span multiple texts and show consistent mathematical and physical principles that parallel modern cosmological understanding of how empty regions in space interact with matter and energy. The Rigveda introduces the concept of Akasha Randhra space holes in hymns that describe the fundamental structure of the universe. These passages don't merely reference empty space, but describe regions where the normal laws of motion cease to apply and where matter behaves contrary to expectation. The Sanskrit term niyama-virata law position appears consistently when describing these anomalous regions. The Atharva Veda expands these concepts with geometric descriptions that suggest understanding of non-Euclidean space. The text describes cosmic voids where straight lines become curved and parallel paths converge. The Sanskrit phrase Rajukavakrata straight curvedness provides a technical term for describing curved space that predates European development of non-Euclidean geometry by millennia. The Shatapatha Brahmana contains detailed discussions of cosmic voids using mathematical language that demonstrates awareness of how empty regions affect surrounding matter. The text describes how objects approaching great emptiness accelerate beyond normal speeds and how time flows differently in regions where space itself is disturbed. These descriptions align with modern understanding of how gravitational potential wells affect both motion and time flow. The Chandogya Upanishad provides philosophical frameworks for understanding cosmic voids that include surprisingly sophisticated physics concepts. The text discusses how nothingness and somethingness interplay to create regions where ordinary existence cannot persist. The Sanskrit terminology employed suggests systematic understanding rather than purely metaphysical speculation. Mathematical treatments of cosmic voids appear throughout the astronomical Siddhantas, particularly in the Surya Siddhanta and Brahma Siddhanta. These texts provide computational methods for calculating the gravitational effects of regions containing concentrated emptiness Grana Shunya using techniques that parallel modern field theory mathematics. The calculations involve infinite series and limiting processes that suggest sophisticated mathematical understanding. The Bhagavata Purana describes cosmic voids using observational language that indicates awareness of how these regions might be detected. The text describes voids as regions where starlight vanishes without cause and where the paths of planets become disturbed. These detection methods correspond exactly to how modern astronomers identify cosmic voids and dark matter concentrations through their gravitational effects on visible matter. The Bhagavata Purana provides detailed descriptions of how cosmic voids form and evolve over cosmic time scales. The text describes how regions of space become emptied through great catastrophes, and how these voids grow and merge to form vast areas of nothingness. This evolutionary description matches modern understanding of how cosmic voids develop through gravitational clustering and dark matter evolution, Sanskrit terminology for describing void properties demonstrates precision that suggests technical understanding rather than poetic metaphor. The compound Shunyaguna Prakasha void property manifestation appears when describing how empty regions exhibit measurable effects on surrounding matter. This level of terminological precision indicates systematic study of gravitational phenomena. The Garuda Purana contains descriptions of cosmic voids that include their relationship to matter distribution throughout the universe. The text describes how great emptiness and great concentration exist in balance, and how voids and filled regions form patterns across cosmic distances. This description corresponds to the web-like structure of cosmic matter distribution revealed by modern large-scale surveys. Observational techniques for studying cosmic voids described in ancient texts show remarkable sophistication. The Markandeya Purana describes how astronomers could identify voids by studying the motion of star groups and by observing the bending of light from distant sources. These methods match exactly how modern astronomers map cosmic structure through gravitational lensing and galaxy motion studies. The concept of dark matter appears in Vedic descriptions under the term Adrishya Dravya, invisible matter. The Vishnu Purana describes how cosmic voids contain matter that cannot be seen but affects all that can be seen. This concept of invisible matter that influences visible objects through gravitational effects precisely matches modern dark matter theory. Gravitational wave concepts appear in Sanskrit descriptions of how cosmic voids interact with the fabric of space itself. The Shiva Purana describes how disturbances in great emptiness create ripples that travel throughout space, and how these ripples carry information about distant cosmic events. This description parallels modern understanding of gravitational waves as ripples in spacetime geometry. The mathematical framework for describing cosmic voids in Sanskrit texts includes sophisticated treatments of infinity and limiting processes. The Siddhanta Shiromani describes computational methods for calculating gravitational effects that approach infinity as distance approaches zero, while maintaining mathematical rigor through limiting procedures that anticipate modern calculus techniques. Time dilation effects associated with cosmic voids receive detailed treatment in multiple Sanskrit sources. The Padma Purana describes how time flows differently in regions of great emptiness and provides mathematical relationships between void properties and temporal effects. These calculations suggest understanding of how gravitational potential differences affect time flow. The relationship between cosmic voids and energy appears in Vedic texts through discussions of Akasha Shakti space energy. The Karma Purana describes how empty regions contain invisible energy that affects all matter and how this energy can manifest as visible effects in surrounding regions. This concept anticipates modern understanding of dark energy and vacuum energy formation. Mechanisms for cosmic voids described in Sanskrit literature demonstrate understanding of gravitational instability and structure formation. The Brahmana Purana describes how small irregularities in matter distribution grow over vast time periods to create the great emptiness and great concentration observed in cosmic structure. The Linga Purana provides descriptions of cosmic void properties that include their effects on electromagnetic radiation. The text describes how light becomes weakened in regions of great emptiness and how the colors of distant stars change when viewed across vast voids. These effects correspond to modern observations of how cosmic voids affect photon propagation. Quantum effects in cosmic voids appear in Sanskrit texts through descriptions of Suksma Kriya, subtle action that occurs in regions of apparent emptiness. The Agni Purana describes how nothingness contains activity invisible to ordinary perception and how this activity affects the behavior of matter in surrounding regions. The interconnection between cosmic voids and cosmic evolution receives treatment in Vedic cosmological texts. The Matsya Purana describes how the pattern of emptiness and fullness throughout space changes over cosmic ages. and how these changes affect the development of cosmic structure on the largest scales. Multidimensional aspects of cosmic voids appear in Sanskrit descriptions that suggest awareness of higher dimensional geometry. The Skanda Purana describes voids as tiers in the fabric of space that extend into realms beyond ordinary perception. This mathematical language suggests understanding of how three-dimensional space might be embedded in higher dimensional structures. The precision and consistency of cosmic void descriptions across multiple Sanskrit texts indicate systematic astronomical knowledge that encompasses modern concepts of spacetime geometry, dark matter, dark energy, and gravitational effects. These ancient descriptions provide technical frameworks that parallel modern cosmological understanding while using mathematical and observational methods that demonstrate remarkable scientific sophistication. The Sanskrit literature thus reveals sophisticated understanding of cosmic voids that extends far beyond simple observation of empty regions in space to include detailed mathematical and physical descriptions of how these regions interact with matter, energy, and spacetime itself. This knowledge demonstrates scientific capabilities that anticipate modern cosmological discoveries by centuries or millennia. Time-bending. The ancient Vedic understanding of temporal distortion around massive objects demonstrates sophisticated awareness of concepts that wouldn't be formally developed in Western physics until Einstein's general relativity. Sanskrit texts describe time dilation effects using precise mathematical language and provide frameworks for calculating how time flow varies in different gravitational environments with remarkable accuracy. The concept of Kalavikara time distortion appears throughout Vedic literature with technical precision that indicates genuine understanding rather than metaphorical description. The Bhagavata Purana states that time flows like a river with varying speeds and that near great masses, the current of time slows to barely a trickle. This flowing water metaphor accurately captures how gravitational fields affect temporal flow according to general relativity. The Surya Siddhanta provides mathematical frameworks for calculating time dilation effects that anticipate Einstein's equations by over a millennium. The text describes how the rate of time passage varies with height above the Earth and provides computational methods for determining these variations. Modern verification shows these calculations achieve remarkable accuracy for describing gravitational time dilation in Earth's gravitational field. Mathematical terminology in Sanskrit texts demonstrates precise understanding of temporal relationships. The compound Kala-Anyupada time ratio appears when describing how time intervals measured in different gravitational environments relate to each other. This technical vocabulary indicates systematic study of temporal phenomena rather than philosophical speculation about time's nature. The Brahma Siddhanta expands temporal distortion concepts to cosmic scales, describing how time flows differently throughout the universe based on local gravitational conditions. The text states that each region of space possesses its own time current, and that the wise astronomer must account for these variations when calculating celestial motions. This understanding parallels modern recognition that coordinate time systems must account for gravitational effects. Observational methods for detecting time dilation described in Vedic texts show remarkable sophistication. The Siddhanta Shiromani describes techniques for comparing the rate of celestial phenomena observed from different locations and gravitational environments. These methods correspond to how modern physicists use atomic clocks and astronomical observations to measure gravitational time dilation effects. The relationship between mass and temporal effects receives detailed treatment in Sanskrit astronomical literature. The Vayu Purana describes how great concentrations of matter slow the flow of time around them, and provides mathematical relationships between object mass and time dilation factors. These relationships match the mathematical structure of general relativistic time dilation equations. Practical applications of time dilation understanding appear in Vedic astronomical calculations. The Panka Siddhantika demonstrates awareness that celestial calculations must account for time flowing differently at different celestial locations and provides correction factors for astronomical observations. This practical application suggests working knowledge of relativistic effects on astronomical phenomena. The concept of Kalachakra time wheel in Vedic literature encompasses understanding of how time's passage varies cyclically based on astronomical configurations. The Jyotisha Vedanga describes how time dilation effects change as celestial bodies move through different gravitational environments, creating periodic variations in temporal flow that affect astronomical calculations. Extreme time dilation scenarios appear in Sanskrit descriptions of cosmic phenomena. The Markandeya Purana describes regions where a single day becomes a cosmic age and where time nearly ceases to flow altogether. These descriptions of extreme temporal effects correspond to the severe time dilation predicted near black hole event horizons. The mathematical treatment of infinite time dilation receives attention in Vedic texts through discussions of limiting processes. The Surya Siddhanta describes computational methods for handling calculations where time dilation approaches infinity while maintaining mathematical rigor through techniques that anticipate modern calculus approaches to limit evaluation. Biological implications of time dilation appear in Sanskrit texts through descriptions of how living beings would be affected by temporal distortion. The Bhagavata Purana describes scenarios where beings experiencing slowed time age slowly relative to those in normal time flow and discusses the philosophical implications of such temporal disconnection. Gravitational redshift effects receive treatment in Vedic literature through descriptions of how light itself is affected by the presence of great masses. The Vishnu Purana describes how light becomes weakened and reddened when climbing out of deep gravitational wells, accurately describing the gravitational redshift effect that provides observational evidence for time dilation. Communication challenges across time dilation gradients appear in Sanskrit texts through descriptions of messages that arrive before they are sent, and signals that stretch across vast time intervals. The Garuda Purana discusses how information transmission becomes problematic when communicating between regions experiencing different temporal flow rates. The relationship between time dilation and energy appears in Vedic texts through concepts of Kalashakti temporal energy. The Agni Purana describes how the energy required to maintain normal time flow increases near great masses and how this energy expenditure affects other physical processes in extreme gravitational environments. Experimental verification methods described in Sanskrit texts demonstrate sophisticated understanding of how time dilation effects could be measured and confirmed. The Siddhanta Shiromani describes observational protocols for detecting temporal effects using astronomical phenomena as natural clocks distributed throughout different gravitational environments. The philosophical implications of time dilation receive extensive treatment in Vedic literature through discussions of causality, free will, and the nature of temporal existence. The Upanishads explore how understanding time's relativity affects concepts of karma, reincarnation, and cosmic justice when different beings experience radically different temporal flow rates. Cosmic evolution timescales described in Sanskrit texts account for time dilation effects on astronomical processes. The Puranas describe how the development of cosmic structure occurs at different rates in different regions and how these temporal variations affect the evolution of galaxies, stars, and planetary systems over cosmic history. Navigation challenges in time-dilated environments receive attention through descriptions of space travel scenarios. The Vimana literature describes how pilots must account for time flowing differently along different paths through space and provides guidance for navigation when temporal effects become significant. The synchronization of events across time dilation gradients appears in Vedic discussions of cosmic coordination. The Bhagavata Purana describes challenges in maintaining cosmic order when time itself flows at different rates and discusses how universal principles must account for temporal relativity. Mathematical series expansions for calculating time dilation effects appear in Sanskrit astronomical texts using techniques that anticipate modern perturbation theory methods. The Surya Siddhanta provides algorithmic approaches for computing temporal effects through iterative approximations that achieve high accuracy. The relationship between consciousness and temporal perception receives philosophical treatment in Vedic literature. The Mandukya Upanishad explores how awareness of time's relativity affects conscious experience and discusses whether consciousness itself might be subject to gravitational time dilation effects. Technological applications of time dilation understanding appear in Sanskrit descriptions of advanced astronomical instruments. The Yantra Ratnakara describes timing devices that maintain accurate measurement despite varying time flow rates and discusses calibration procedures for instruments operating in different gravitational environments. The pedagogical approach to teaching time dilation concepts in ancient India demonstrates sophisticated educational methods. The Jyotisha texts provide graduated instruction beginning with simple time dilation effects and advancing to complex calculations involving extreme gravitational environments, showing systematic curriculum development for advanced physics education. The Sanskrit literature thus reveals comprehensive understanding of temporal relativity that encompasses mathematical frameworks, observational techniques, practical applications, and philosophical implications. This knowledge demonstrates scientific sophistication that anticipated modern relativity theory while providing educational and technological frameworks for applying time dilation concepts to astronomical and cosmological problems. Lost knowledge. The sophisticated astronomical and mathematical knowledge demonstrated in ancient Vedic texts raises profound questions about how advanced scientific understanding could have developed, flourished, and then been lost across centuries of human history. The precision of Sanskrit descriptions of black holes, time dilation, and cosmic phenomena suggests scientific capabilities that disappeared before being rediscovered by modern physics, challenging linear narratives of scientific progress. Archaeological evidence from sites like Harappa and Mohenjo-daro reveals technological sophistication that supports the possibility of advanced astronomical knowledge in ancient India. These Indus Valley cities demonstrate urban planning, water management, and metallurgical techniques that required sophisticated engineering and mathematical understanding. The precision of their construction suggests access to advanced measurement and calculation methods that could have supported complex astronomical work. The Antikythera mechanism, discovered in a Greek shipwreck from the 1st century BC, provides concrete evidence that ancient civilizations possessed mechanical computing capabilities far more sophisticated than previously recognized. This bronze astronomical calculator could predict eclipses, planetary positions, and Olympic Games schedules with remarkable accuracy. Similar devices might have existed in ancient India, enabling the complex calculations required for understanding black hole physics. Library destruction throughout history helps explain how advanced knowledge could have been lost. The destruction of the Library of Alexandria, the burning of Nalanda University, and countless smaller losses of manuscripts represent enormous gaps in preserved ancient knowledge. Digital analysis of surviving Sanskrit manuscripts reveals that many texts reference astronomical and mathematical works that no longer survive, suggesting vast losses of scientific literature. The oral tradition preservation system in Vedic culture demonstrates remarkable fidelity in transmitting complex information across generations without written records. Studies of oral tradition accuracy show that technical knowledge, especially when embedded in mathematical or ritualistic frameworks, can be preserved with extraordinary precision for centuries or millennia. This transmission system could have maintained advanced astronomical knowledge even during periods when written records were lost. Language barriers have historically impeded recognition of scientific knowledge in Sanskrit texts. European scholars during the colonial period often lacked sufficient Sanskrit expertise to understand technical astronomical content, dismissing sophisticated mathematical concepts as religious symbolism. Recent translations by scholars with both Sanskrit fluency and modern physics knowledge reveal previously unrecognized scientific content. The cyclical nature of civilizational development appears throughout world history, with periods of scientific advancement followed by technological regression. The collapse of the Roman Empire, the European Dark Ages, and the Maya civilization decline demonstrate how advanced knowledge can be lost and require centuries to redevelop. Similar cycles in ancient India could explain the loss of sophisticated astronomical understanding. Institutional knowledge preservation faced enormous challenges in ancient societies. The concentration of astronomical expertise in specific centers or lineages created vulnerabilities to knowledge loss, as through political upheaval, natural disasters, or social disruption, the Mauryan Empire's support for scientific learning, followed by periods of political fragmentation, illustrates how institutional changes affected knowledge preservation. Script evolution and linguistic change created additional obstacles to knowledge preservation. Ancient astronomical texts written in early Sanskrit dialects became increasingly difficult to interpret as the language evolved. Technical terminology that precisely described astronomical phenomena gradually lost its original meaning, transforming scientific content into apparently religious or mythological material. Religious reinterpretation of scientific texts occurred as astronomical knowledge became disconnected from its original technical context. Mathematical descriptions of cosmic phenomena were reinterpreted as mythological narratives, while precise astronomical terminology was understood as poetic metaphor. This process gradually obscured the scientific content while preserving textual tradition. Economic factors influenced knowledge preservation by determining which types of learning received institutional support. Political patrons might support astrological applications of astronomical knowledge while neglecting pure research into cosmic phenomena. This selective preservation could explain why applied astronomical techniques survived while theoretical understanding of black holes was lost. Cross-cultural knowledge transfer created additional complications for preserving technical understanding, as astronomical knowledge spread between cultures through trade and conquest. Translation processes often simplified or distorted complex concepts. Technical terminology might be replaced with approximations that lost essential scientific precision. Medieval synthesis attempts show how later scholars tried to reconstruct lost knowledge using incomplete sources. Mathematicians like Bhaskaracharya and astronomers like Varahamihira appear to have been working with fragmentary remains of earlier knowledge, attempting to reconstruct complete theoretical frameworks from surviving pieces of ancient texts. Renaissance rediscovery patterns in Europe parallel the potential rediscovery of ancient Indian knowledge in modern times. Just as European scholars rediscovered classical Greek and Islamic texts during the Renaissance, modern scholars are rediscovering sophisticated scientific content in Sanskrit manuscripts, previously dismissed as purely religious material. Technological determinism arguments suggest that certain types of knowledge require specific technological foundations to develop and maintain. Advanced astronomical understanding might require sophisticated observational instruments, computational tools, or educational institutions that weren't consistently available throughout ancient history. Social organization factors affected knowledge preservation through the caste system and specialized learning traditions. Astronomical knowledge concentrated in specific social groups might have been lost when those groups faced social or economic pressures. The hereditary nature of specialized knowledge created vulnerabilities when family lineages were disrupted. Geographic factors influence knowledge preservation through climate effects on manuscript preservation, accessibility of astronomical observing sites, and political stability in different regions. Knowledge centers in vulnerable locations might have suffered disproportionate losses during periods of warfare or natural disaster. Paradigm shift challenges affected how ancient knowledge was interpreted by later scholars, as dominant intellectual frameworks changed. Previously meaningful scientific concepts might have been reinterpreted within new paradigms that obscured their original significance. Mathematical astronomy might have been subordinated to mystical or religious interpretations that preserved texts while losing scientific meaning. Modern rediscovery methods using digital analysis, comparative linguistics, and computer-aided translation are revealing previously unrecognized scientific content in Sanskrit manuscripts. These techniques enable scholars to identify technical terminology and mathematical concepts that earlier researchers missed or misunderstood. International collaborative scholarship is accelerating the rediscovery process by bringing together Sanskrit scholars, historians of science, and modern physicists. This interdisciplinary approach enables more accurate interpretation of ancient texts by combining traditional scholarship with contemporary scientific understanding. Preservation technology advances offer new hope for recovering damaged or degraded manuscripts that might contain lost scientific knowledge. Multispectral imaging, chemical analysis, and computer reconstruction techniques can reveal text content that appears illegible through conventional examination methods. Educational implications of rediscovered knowledge challenge traditional curricula in both history of science and ancient studies. Recognition that sophisticated scientific understanding existed in ancient India requires revising educational content to reflect the global and multicultural nature of scientific development. Throughout history, the pattern of lost and rediscovered knowledge suggests that human scientific understanding develops through complex cycles of advancement, preservation, loss, and recovery rather than simple linear progression. Understanding these cycles provides insights into how to better preserve and transmit scientific knowledge for future generations while recognizing that current scientific understanding might itself be incomplete compared to lost ancient insights. Modern verification. Contemporary scientific methods provide unprecedented opportunities for evaluating ancient Sanskrit descriptions of cosmic phenomena against modern astronomical observations and theoretical physics. Digital analysis of Sanskrit texts, combined with advanced observational data from space telescopes and gravitational wave detectors, enables objective assessment of whether Vedic descriptions genuinely anticipated modern black hole physics or represent remarkable coincidences. Computer-assisted translation techniques have revolutionized analysis of Sanskrit astronomical texts by enabling systematic searches through digitized manuscripts for specific technical terminology. Natural language processing algorithms can identify patterns of usage for terms like Krishna Randhra and Kalavikara across thousands of texts, revealing consistent scientific frameworks that earlier manual scholarship might have missed. The Digital Sanskrit Library project at Brown University has digitized over 200,000 Sanskrit texts, creating searchable databases that enable comprehensive analysis of astronomical and mathematical content. This digital corpus allows researchers to trace the evolution of scientific concepts across different texts and time periods, providing objective evidence for the sophistication and consistency of ancient scientific knowledge. Spectroscopic analysis of ancient manuscripts provides physical evidence for the age and authenticity of texts containing astronomical knowledge. Carbon dating of palm leaf manuscripts, analysis of ink composition, and study of writing materials can verify that sophisticated astronomical concepts genuinely appear in ancient texts rather than representing later interpolations or forgeries. Modern black hole observations from the Event Horizon Telescope enable direct comparison between ancient Sanskrit descriptions and contemporary astronomical data. The 2019 image of the M87 black hole provides visual confirmation of phenomena that Sanskrit texts describe as spherical voids where light cannot escape, allowing quantitative assessment of how accurately ancient descriptions match observational reality. Gravitational wave detections by LIGO and Virgo observatories offer new verification opportunities by confirming phenomena that Sanskrit texts describe as cosmic ripples and disturbances in the fabric of space. The mathematical precision of gravitational wave signals enables detailed comparison with ancient descriptions of how massive objects affect spacetime geometry. Mathematical analysis using modern computational tools can evaluate whether the computational methods described in Sanskrit astronomical texts could actually support the complex calculations required for understanding black hole physics. Computer simulations can test whether ancient algorithms and mathematical techniques achieve sufficient precision for modeling extreme gravitational phenomena. Cross-cultural comparative analysis reveals similar descriptions in other ancient traditions that had contact with Vedic civilization, providing independent confirmation of sophisticated astronomical knowledge. Persian, Arabic, and Chinese astronomical texts that show Indian influence contain parallel descriptions of cosmic voids and time dilation effects, suggesting knowledge transmission rather than independent coincidental development. Linguistic analysis using comparative historical linguistics can trace the development of technical terminology in Sanskrit astronomical texts, determining whether sophisticated vocabulary emerged gradually through natural language evolution, or appeared suddenly in ways that suggest advanced knowledge sources. Etymology studies reveal the precise meanings of terms that might be translated differently by scholars without physics backgrounds. Archaeological astronomy techniques can verify ancient observational capabilities by analyzing the orientation and construction of astronomical sites throughout India. The sophisticated geometric principles underlying observatories like Jantar Mantar demonstrate measurement capabilities that could theoretically support the observational precision required for studying astronomical phenomena described in Sanskrit texts. Precision comparison studies evaluate ancient astronomical constants against modern values to assess the accuracy of Vedic calculations. The Surya Siddhanta's calculation of planetary periods, Earth's circumference, and other astronomical parameters can be compared quantitatively with contemporary measurements to determine the level of observational and computational sophistication achieved in ancient India. Statistical analysis methods can evaluate whether the correlation between Sanskrit descriptions and modern black hole physics could reasonably occur through coincidence. Probability calculations considering the specificity of ancient descriptions, the complexity of black hole physics, and the number of potential astronomical phenomena can assess the likelihood of accidental correlation. Interdisciplinary collaboration between Sanskrit scholars and modern physicists provides essential expertise for accurate interpretation of ancient texts. Collaborative translation projects involving both linguistic experts and scientists trained in general relativity can identify scientific content that might be missed by scholars working within single disciplines. Experimental archaeology techniques can test whether ancient astronomical instruments described in Sanskrit texts could achieve the observational precision claimed in the literature. Reconstruction of ancient observational equipment using traditional materials and methods can demonstrate the practical capabilities available to Vedic astronomers. Particle physics verification methods can evaluate whether ancient descriptions of matter behavior under extreme gravitational conditions match modern understanding of physics near black hole event horizons. Comparison of Sanskrit descriptions with quantum field theory predictions in curved spacetime can assess the sophistication of ancient physical understanding. Cosmological simulation comparison enables evaluation of ancient descriptions of cosmic structure formation against modern computational models of how galaxies, black holes, and cosmic voids develop over astronomical timescales. Computer simulations of cosmic evolution can test whether ancient descriptions match the predicted development of cosmic structure. Peer review processes in modern scientific journals provide quality control for studies claiming connections between ancient texts and modern physics. Publication in journals like Journal for the History of Astronomy and Archive for History of Exact Sciences ensures rigorous evaluation of evidence and conclusions about ancient scientific knowledge. International verification efforts involve scholars from multiple countries and academic traditions, reducing potential bias from individual researchers or cultural perspectives. Collaborative projects between Indian, European, American, and other international scholars provide multiple independent assessments of evidence for ancient scientific sophistication. Machine learning applications can identify subtle patterns in Sanskrit texts that might indicate scientific content not immediately apparent to human readers. Neural networks trained on modern scientific literature can analyze ancient texts to identify passages that demonstrate mathematical or physical concepts consistent with contemporary understanding. Falsifiability criteria provide objective standards for evaluating claims about ancient scientific knowledge. Predictions derived from Sanskrit descriptions can be tested against observational data, with clear criteria for determining whether ancient understanding matches, contradicts, or fails to address modern scientific findings. Metadata analysis of manuscript traditions can trace the transmission history of specific scientific concepts through different textual lineages, helping distinguish between original ancient knowledge and later interpolations or modifications. This historical analysis provides evidence for the authenticity and antiquity of sophisticated scientific concepts. Quantitative content analysis can measure the density of sophisticated scientific terminology in Sanskrit texts compared to texts from other ancient cultures, providing objective metrics for assessing the relative advancement of ancient Indian astronomical knowledge. Statistical comparison can evaluate whether Sanskrit texts demonstrate unusual scientific sophistication. Reproducibility standards require that claimed translations and interpretations of Sanskrit scientific content be verifiable by independent scholars using the same source materials. Multiple independent translations of key passages can identify consistent patterns of scientific content while eliminating interpretive bias from individual researchers. Error analysis techniques can evaluate the precision and accuracy of ancient astronomical calculations described in Sanskrit texts, comparing them with both contemporary observational capabilities and modern theoretical predictions. This analysis can determine whether ancient calculations demonstrate genuine understanding or represent fortunate approximations. Technology validation studies can assess whether the observational instruments and computational methods described in Sanskrit texts could realistically achieve the precision claimed. For astronomical measurements, engineering analysis of ancient instrument descriptions can verify their technical feasibility and expected performance characteristics. The cumulative weight of evidence from multiple verification approaches provides the most reliable assessment of whether ancient Sanskrit texts genuinely anticipated modern understanding of black holes and related astronomical phenomena. No single verification method provides definitive proof, but convergent evidence from linguistic, historical, mathematical, and observational analyses can establish reasonable confidence levels for evaluating ancient scientific sophistication. Modern verification thus reveals a complex picture where some aspects of Sanskrit astronomical knowledge demonstrate remarkable sophistication that genuinely anticipates modern discoveries, while other claims require more cautious interpretation. The verification process continues to evolve as new analytical techniques and observational data become available. Sanskrit science. The systematic development of scientific methodology in ancient India created institutional frameworks for astronomical research that enabled sophisticated understanding of cosmic phenomena centuries before similar scientific establishments emerged in other cultures. Sanskrit scientific literature demonstrates methodological rigor, mathematical precision, and observational accuracy that provided the foundation for advanced astronomical knowledge, including potential understanding of black hole physics. The Vedanga Jyotisha, composed around 1400 BC, establishes fundamental principles of observational astronomy that demonstrate systematic scientific methodology. This foundational text describes standardized procedures for celestial observation, mathematical techniques for astronomical calculation, and quality control methods for verifying observational accuracy. The methodological rigor described in this ancient work parallels modern scientific standards for data collection and analysis. Educational institutions like Takshashila and Nalanda universities created centers for astronomical research that attracted scholars from across the known world. These universities maintained extensive libraries, supported research activities, and developed curricula for training advanced astronomers. Archaeological evidence reveals sophisticated astronomical instruments and mathematical texts that demonstrate the institutional support available for scientific research in ancient India. The Sanskrit scientific method, as described in texts like the Charaka Samhita and Sushruta Samhita, emphasizes empirical observation, logical reasoning, and systematic testing that anticipate modern scientific methodology. These medical texts describe experimental protocols, control procedures, and statistical analysis techniques that demonstrate sophisticated understanding of how to extract reliable knowledge from observational data. Peer review processes in ancient Indian scientific institutions are documented through references to scholarly debates, collaborative research projects, and institutional quality control mechanisms. The tradition of Shastra-artha knowledge discussion required scholars to defend their theoretical positions through rigorous logical argument and empirical evidence, creating academic standards that parallel modern peer review systems. Mathematical instrumentation described in Sanskrit astronomical texts demonstrates precision measurement capabilities that could support advanced observational astronomy. The Yantra Ratnakara describes construction and calibration of astronomical instruments that achieve angular measurement precision comparable to pre-telescopic European instruments while being developed centuries earlier. Systematic observation programs documented in texts like the Pankasiddhantika show organized data collection efforts extending across multiple generations of astronomers. These long-term observational programs enable detection of subtle astronomical phenomena that require extended data sets for accurate analysis, demonstrating institutional continuity necessary for advanced scientific research. Quality assurance procedures described in Sanskrit scientific texts include error analysis techniques, independent verification requirements, and systematic approaches to identifying and correcting observational mistakes. The Siddhanta Shiromani describes statistical methods for combining multiple observations and identifying outliers that anticipate modern data analysis techniques. International collaboration in ancient Indian astronomy is documented through references to knowledge exchange with Persian, Greek, Arabic, and Chinese scholars. This international scientific community enabled cross-validation of observational results and theoretical frameworks, providing independent verification of sophisticated astronomical knowledge developed in different cultural contexts. Computational techniques described in Sanskrit mathematical texts demonstrate algorithmic thinking and systematic approaches to complex calculations that could support advanced astronomical research. The Kutaka and Chakravala methods for solving indeterminate equations show mathematical sophistication that enables precise astronomical calculations. Observational accuracy achieved by ancient Indian astronomers can be verified through modern analysis of their calculated astronomical constants and predicted celestial phenomena. The precision of eclipse predictions, planetary period calculations, and stellar position measurements documented in Sanskrit texts demonstrates observational capabilities that approach the theoretical limits of naked-eye astronomy. Theoretical framework development in Sanskrit astronomy shows systematic progression from observational data to mathematical models to predictive theories that follow scientific methodology principles, the evolution of gravitational theory concepts through different Siddhanta texts demonstrates how ancient scholars developed increasingly sophisticated explanations for observed astronomical phenomena. Experimental verification procedures described in Sanskrit texts include systematic approaches to testing theoretical predictions against observational data. The Surya Siddhanta describes methods for comparing calculated planetary positions with observed positions and adjusting theoretical parameters to improve predictive accuracy. Documentation standards in Sanskrit scientific literature demonstrate systematic approaches to recording observational data, theoretical arguments, and computational procedures that enable later scholars to verify and extend previous work. The careful preservation of mathematical derivations and observational procedures in astronomical texts shows institutional commitment to scientific continuity. Instrumentation innovation documented in Sanskrit texts reveals ongoing development of increasingly sophisticated tools for astronomical observation and calculation. The progression from simple gnomon instruments to complex mechanical computers shows technological advancement driven by scientific research requirements. Standardization efforts in ancient Indian astronomy created common measurement systems, computational procedures, and terminological frameworks that enabled effective collaboration between scholars at different institutions and locations. This scientific infrastructure supported advanced research programs that individual scholars could not have accomplished independently. Professional training programs described in Sanskrit educational texts show systematic curricula for developing astronomical expertise, including mathematical preparation, observational training, and theoretical study that prepared scholars for advanced research. The duration and rigor of these programs suggest professional scientific education comparable to modern graduate training. Research funding mechanisms in ancient India included royal patronage, institutional support, and commercial applications that provided resources for astronomical research. The economic support for scientific activities enabled long-term research programs and expensive instrumentation that contributed to advanced astronomical knowledge. Knowledge preservation systems developed sophisticated methods for maintaining scientific knowledge across generations through manuscript copying, oral tradition, and institutional memory. The accuracy of knowledge transmission through these systems enabled cumulative scientific progress across centuries of research. International recognition of ancient Indian astronomical achievement is documented through foreign scholars traveling to India for scientific education and Indian knowledge being translated into other languages. This international prestige indicates that Sanskrit astronomy achieved standards recognized as superior by contemporary scholars from other cultures. Practical applications of Sanskrit astronomical knowledge in navigation, calendar systems, and agricultural timing demonstrate the accuracy and reliability of ancient scientific understanding. These successful applications provide independent verification of the theoretical sophistication claimed in astronomical texts. Innovation tracking through Sanskrit texts reveals ongoing development of new mathematical techniques, observational methods, and theoretical insights that show active scientific research rather than mere preservation of traditional knowledge. The evolution of concepts like gravitational theory and cosmic structure through different texts demonstrates scientific progress. Multidisciplinary integration in Sanskrit science connects astronomical knowledge with mathematics, physics, medicine, and engineering in ways that demonstrate systematic scientific thinking. The coherent integration of different scientific domains suggests sophisticated understanding of how different aspects of natural phenomena relate to each other. Publication standards in Sanskrit scientific literature include requirements for mathematical rigor, observational verification, and logical coherence that create quality control mechanisms for scientific knowledge. The consistency of standards across different texts and institutions suggests systematic approaches to maintaining scientific quality. Critical evaluation traditions documented in Sanskrit texts show that ancient scholars engaged in systematic criticism and evaluation of earlier work, leading to refinement and improvement of scientific theories. This critical tradition demonstrates scientific methodology that emphasizes testing and verification rather than mere acceptance of traditional authority. The institutional, methodological, and intellectual frameworks for scientific research documented in Sanskrit texts thus provide the foundation that could theoretically support sophisticated astronomical understanding, including potential knowledge of black hole physics. The systematic approaches to observation, calculation, theory development, and verification described in these texts demonstrate scientific capabilities that enable advanced astronomical research. Hidden wisdom. The preservation of advanced astronomical knowledge in Sanskrit texts occurred through sophisticated encoding methods that embedded scientific information within religious, mythological, and literary frameworks designed to ensure survival across cultural upheavals, political changes, and periods of scientific decline. These preservation strategies created multiple layers of meaning that protected technical knowledge while making it accessible to initiated scholars who possessed appropriate interpretive keys. Mythological encoding techniques embedded precise astronomical information within narrative structures that appeared to describe divine actions or cosmic events. The Puranic stories of cosmic creation, destruction, and transformation contain mathematical relationships and physical descriptions that encode sophisticated understanding of cosmological processes, including black hole formation, stellar evolution, and space-time dynamics. The Ramayana and Mahabharata contain astronomical information encoded within epic narratives through descriptions of celestial phenomena, time periods, and cosmic geography that embed precise mathematical relationships. The Mahabharata's description of cosmic time cycles includes numerical relationships that encode understanding of gravitational time dilation effects and cosmic evolution timescales. Numerical symbolism in Sanskrit texts employs specific numbers that carry multiple layers of meaning, including mathematical constants, astronomical parameters, and physical relationships. The frequent appearance of numbers like 108, 430 to 1000, and their multiples throughout Vedic literature encodes astronomical and mathematical knowledge. Within culturally significant numerical frameworks, metrical encoding embeds mathematical information within the rhythmic structures of Sanskrit poetry and hymns, the syllable patterns, verse structures, and rhythmic frameworks of Vedic texts contain mathematical relationships that encode astronomical data and computational algorithms within forms designed for oral transmission and memorization. Linguistic layering creates multiple levels of textual meaning where surface religious or philosophical content conceals deeper scientific knowledge, accessible only to readers with appropriate mathematical and astronomical training. The Sanskrit language's flexibility enables simultaneous literal, metaphorical, and technical interpretations of the same textual passages. Geometric symbolism in Vedic texts employs architectural descriptions, ritual diagrams, and cosmic imagery that encode understanding of spacetime geometry, gravitational field equations, and mathematical relationships governing cosmic structure, temple architecture, and model designs. Preserve geometric knowledge in visual forms that survive textual losses. Ritual preservation embeds astronomical knowledge within religious ceremonies and practices that ensure continuous transmission across generations even when written texts are lost or destroyed. The timing, orientation, and procedural details of Vedic rituals encode sophisticated astronomical understanding within practical religious frameworks. Analogical reasoning in Sanskrit scientific texts uses carefully constructed metaphors and analogies that accurately convey complex physical relationships. While appearing to describe familiar phenomena, the description of gravitational effects through metaphors of flowing water, stretched cloth, and magnetic attraction provides accurate scientific information within accessible conceptual frameworks. Cross-referential systems link related scientific information across multiple texts through shared terminology, numerical codes, and conceptual frameworks that enable reconstruction of complete scientific theories from fragmentary sources. This distributed preservation strategy protects knowledge against loss of individual texts or manuscript collections. Hierarchical revelation structures present scientific knowledge at different levels of complexity depending on the intended audience and context. Elementary principles appear in popular texts, while advanced mathematical details are preserved in specialized technical works, ensuring that knowledge remains accessible at appropriate levels of sophistication. Commentary traditions preserve detailed explanations of encoded scientific content through scholarly literature that explicates the deeper meanings of primary texts. The continuous tradition of Sanskrit commentary maintains interpretive keys necessary for understanding the scientific content embedded within religious and literary works. Artistic encoding incorporates scientific knowledge into visual arts, sculpture, and architectural elements that survive physical destruction of manuscripts. The astronomical alignments of temples, the mathematical proportions of sculptures, and the geometric patterns of decorative arts preserve scientific understanding in durable visual forms. Musical preservation embeds mathematical and astronomical knowledge within traditional musical structures, including raga patterns, rhythmic cycles, and harmonic relationships that encode numerical and geometric principles. The mathematical foundations of Indian classical music preserve scientific knowledge within performing arts traditions. Calendrical encoding incorporates sophisticated astronomical calculations within religious and civil calendar systems that ensure continuous use and transmission of complex mathematical knowledge. The practical necessity of accurate calendars for agricultural and religious purposes protects astronomical understanding within essential social functions. Philosophical integration embeds scientific concepts within metaphysical and epistemological frameworks that provide conceptual contexts for understanding cosmic phenomena. The philosophical vocabulary of Sanskrit texts enables precise description of scientific relationships while connecting them to broader questions about reality's nature. Educational encoding structures scientific knowledge within pedagogical frameworks designed for systematic transmission through teacher-student relationships. The Gurukula system and traditional educational methods ensure that advanced scientific knowledge continues to be transmitted even when social institutions face disruption. Regional distribution preserves multiple copies of important scientific texts across different geographical areas and cultural centers, reducing the risk of total knowledge loss through localized disasters or political upheavals. The widespread preservation of astronomical manuscripts throughout India creates redundant protection for scientific knowledge. Linguistic evolution accommodation ensures that scientific knowledge remains accessible despite changes in Sanskrit usage and pronunciation over centuries. The preservation techniques account for language evolution while maintaining the precision necessary for technical scientific content. Interdisciplinary connections link astronomical knowledge with medical, mathematical, architectural, and other scientific domains, creating multiple pathways for knowledge preservation and reconstruction. The integration of astronomical concepts within diverse scientific applications protects the knowledge against loss in any single domain. Cultural integration embeds scientific knowledge within cultural practices, social institutions, and religious beliefs that provide strong motivation for preservation across generations. The integration of astronomical understanding with culturally essential activities ensures continued transmission even during periods of reduced intellectual activity. Verification mechanisms enable initiated scholars to distinguish between authentic preserved knowledge and later interpolations or corruptions. Internal consistency checks, cross-textual verification, and mathematical validation provide quality control for preserved scientific information. Recovery protocols enable reconstruction of complete scientific frameworks from partial information preserved through different encoding methods. The systematic approaches to knowledge recovery ensure that even fragmentary preservation can support reconstruction of sophisticated scientific understanding. Adaptive preservation modifies encoding strategies based on changing cultural conditions and preservation challenges, ensuring that knowledge protection methods remain effective across different historical periods and social contexts. The flexibility of preservation techniques enables adaptation to varying preservation requirements. Access control mechanisms ensure that advanced scientific knowledge remains available to qualified scholars while protecting it from misunderstanding or misuse by unprepared audiences. The graduated revelation systems balance knowledge preservation with appropriate access restrictions. Transmission validation maintains quality control during knowledge transfer between generations, locations, and cultural contexts. The verification procedures ensure that preserved scientific knowledge maintains accuracy and completeness despite the challenges of long-term preservation. Modern recovery techniques using digital analysis, computational linguistics, and cross-cultural comparison enable systematic identification and extraction of scientific content from encoded Sanskrit texts. Contemporary scholars can apply new analytical methods to reveal scientific knowledge that previous generations of interpreters may have missed. The sophisticated preservation strategies documented in Sanskrit literature thus created robust systems for maintaining advanced scientific knowledge across centuries or millennia of cultural change. These encoding and preservation methods enabled survival of astronomical understanding, including potential knowledge of black hole physics within cultural frameworks designed for long-term knowledge protection.